In this video, we're going to look at two questions on magnetic fields. So first of all, it says a beam of protons is accelerated from rest through a potential difference of 2000 volts and enters a uniform magnetic field which is perpendicular to the direction of the proton beam. If the flux density is 0.2 teslas, calculate the radius of the path of the beam. And then it wants us to specify how the result modify for deuterons. Okay, so basically deuterons is just, I think it's just 2, like 1H, yeah. It's a hydrogen with a proton and a neutron, so with a total mass of 2. So, okay, so first of all, what we want to calculate is the radius of the path of the beam. And then one equation is just that mv squared over r, that is centripetal force, is just equal to the magnetic force experienced by the proton as it enters the magnetic field, so that is BQV. And then one thing is that we want to calculate r, and then we are able to know the mass and then the magnetic flux density is given, and also we can know the charge. The only thing we don't know is the velocity, and the velocity can be derived from the potential difference that is given first of all in the question. So one equation that we can utilize is just that QV, so that's charge times potential, is essentially energy, and that is equal to the energy of the proton. So that essentially we assume that all of it converts into kinetic energy, so that's half mv squared, and then we will be able to calculate the velocity of the proton. Okay, so we're going to derive the velocity first. So for the charge of proton, that is the elementary charge, so that is 1.602 times 10 to the negative 19, and then times the potential difference, which is 2000, is equal to a half times the mass of a proton. Now that is given as 1.673, and then times 10 to the negative 27, and then times by the velocity squared. Okay, so the velocity squared will be given as okay, so first of all fraction, and then the elementary charge for a proton, and then times 2000, then times 2 from the other side, and divided by the mass, so that is 673 10 to the negative 7. Now that gives us a rather large number. Yeah, so that is 3.83 times 10 to the this is 10 to the 11. So therefore v will be equal to the square root of this. Now that is just I'm going to say 2 3 decimal places, so that is 6.189 times 10 to the, this is 5 ms minus 1. Okay, and then we're given the velocity now, then we can essentially derive the radius. So over here we can simplify the equation a little bit to make r the subject. So over here the velocities cancel out, and then you time r to the other side, divide bq to the other side, so that what's left will be mv over bq. So therefore r will be equal to the mass of a proton, that is I mentioned before, that is just 10 to the minus 27, and then times the velocity, which we calculate over here, so that's 109, and then times like 10 to the 5, and then b is just 0.2, and then times q, which is essentially elementary charge, and that is to the negative 19. and what gives us is just 0.0. I'm going to say two significant figures, so that's 0.032 meters, and that will be the answer to the question. The radius of the path of the beam. Now, and then it asks us, how's the result modified for deuterons? So let's see. One thing is that, okay, okay, so what I'm going to do is that I'm going to try to combine these two equations so we can get an overall view. So, okay, so let's see. How do we get an overall view? So, I'm going to say, I'm going to derive an equation for velocity. So that will be, velocity will be equal to 2qv over m and square root from the second equation on the right side. And then if we put this into the equation over here, now that will be, r will be equal to m, this whole thing, and then over m, and then bq. So let's see, the only thing that changes is just the mass. And right now it seems that the mass is essentially on the top of the fraction. So this means that if the mass increases, then essentially the radius of the path will increase. So we can basically say that r for the deuteron is basically greater than r for the essentially a single proton. Okay, and then yeah, that is essentially a relationship. And then it says, how do we actually modify the question, the result for it? So I'm going to derive a value as well, and that will be essentially, we can basically directly utilize the equation we derived over here. So if I simplify this a little bit, m over the square root of m is essentially just the square root of m. So on the top we basically have 2qvm in square root and then over bq. And then so we can say like rd will be just equal to, let's see, so a fraction, and then square root, and then 2 times the charge. The charge will still be 1 elementary charge, so that's no change for that. And then 2qv, wait, there's a v. Oh, that's the potential. Yeah, that's a potential. So 2000 and then times the mass. Now the mass, what would be the mass of a proton? I'm going to use the atomic mass unit. So 2 times the atomic mass unit, that will be 2 times 6.67. And then, no, that's not, that is, atomic mass unit is 1.661, and then times 10 to the negative 27. Okay, and then down there we basically have the magnetic flux density, and then you time it by the charge. The charge is just 1 elementary charge, and that will be negative 19. Yeah, and the answer will be simply 0.046 meters, and that will be the answer to the final part of the first question. Now, let's see the second question. Down there it says a horizontal square wire loop of size 4 centimeters has a resistance of this, and then the loop is situated in a vertical downward magnetic field of 0.7 teslas, and when the field is switched off, so the magnetic field is switched off, it decreases to 0 at a uniform rate of 0.8 seconds. Okay, so okay, and then it wants to determine the induced current I. and its direction a loop. Okay, so let's see how can we solve the first part of the question. Once that you calculate the current, so the equation that we need to use is definitely just V is just equal to difference in the magnetic flux over the difference in time. Okay, so let's see what we are given. First of all, horizontal loop side lengths, we were given the side length, and then we given that it is a square, so therefore we can calculate the area. And then we also gave us a resistance, which we can utilize to calculate the current from the voltage. And then we are given the magnetic field, okay? And then we are also given a change of the magnetic field, which is really convenient in this case, okay? So first of all, we can basically separate, not exactly separate, so basically just delta magnetic flux is just equal to delta B times A. Now in this case, the area isn't changing, so it's just the magnetic flux density, so that's just delta B over difference in T. We can move difference in T over with the delta B so that we can express like in the form of the rate of change of magnetic flux density and then times the area. So that will be equal to, we're given, first of all, delta B will be equal to 0.7, and it says delta T is 0.8. That is given because it says like the field is switched off, it decreases to 0 at uniform rate 0.8 seconds. So essentially, what does it mean is that in 0.8 seconds, the magnetic field reduces from 0.7 to 0. So that will be 0.7 over 0.8 for delta B over delta T, and then times the area. Now the area will be, that is 4 centimeters, so that's 0.04 meters, and then squared. And that will be equal to 0.7 over 0.8, and then you time by 0.04 squared. Now that is 0.0014, and it's voltage, so therefore it's in volts. And then let's move on. So we're given the voltage over here, so the thing we want to calculate is just the current. So for current, what we know is that it's equal to voltage over resistance. Now voltage we're given, we already calculated, and then for resistance is given as 2 times 10 to the negative 3, so we can just directly substitute this in and then derive a value for the current. Now the current will be just 0.0014 over minus 3, 0.7 amperes. And then it also wants to calculate the direction of the loop. So to express the direction, I'm going to draw a diagram, okay? So first of all, the loop is some kind of square. So it might look something like this in a three-dimensional view. And then the idea is just that vertical downward magnetic field, so I'm going to draw the magnetic field. So it will look something like this, I would say. Yeah. And then these are the magnetic field lines perpendicular. And you want the direction of the loop. So now this is essentially electromagnetic induction. So what we need to use is essentially the reverse of the right hand rule. So if you utilize the reverse of the right hand rule, it will be given us the direction of the current will be in this direction. Okay, so that will be in the clockwise direction. Okay, so we can say like thus the current flows in the clockwise direction. And then let's see the second part. The second part of the question asks the energy dissipated in the loop. So, okay. The energy dissipated. Let's see. Okay. Okay, so let's see. How do we calculate energy? The energy is equal to VI and then times the time, right? So in the context of this question, we know the V, we know the I, which we both arrived, and then the T, which is just 0.8 seconds. So we know all the values, and then we can just directly calculate it, okay? So that would be just the voltage is, we calculate over here, 0.004, and then times the current, which is 0.7, and then times time, which is given as 0.8. And then that will be just equal to 0.0014 times 0.7 and then times 0.8. And then that will be 7.84 times 10 to the negative 4 seconds. And that will be the answer to the question.